that I've been linking through my web page. It's a YouTube video. So with these people that are gone, they could go to that and they can see and hear what we did in class today. Or if you got stuck on something, you could go to your notes and see what we did. Okay, just to finish up yesterday, the polygon part, towards the end of that, a polygon is a closed plane figure formed by 3 or more line segments. That's a definition we really need to know in our class. We won't be using it for a while, but they gave us a few things to do definitions with so that you can do a few problems on the assignment. So here's some examples of things that were polygons, things that are not polygons. Why isn't this one a polygon? Look at that definition.
Has a curve.
Because it has a curve. This is not all segments. What's wrong with that one?
It's not segments.
Okay, it probably wouldn't be considered closed because it's not connecting at the right place. This would need to connect way out to the end. This one? Now, sometimes students say that's two polygons side by side. I think what they're trying to show is you cannot have segments cross in order to make a polygon because that closes it somewhere other than just the outside edges. So that one doesn't work either. This one? That one's not closed. And how about the 3D shape? Polygons be 3D? What in that definition would tell you that that's not? Okay, the word plane. Plane doesn't mean just simple. Plane means flat. Okay? So it's a closed flat figure formed by 3 or more line segments. So there were polygons and things that are not polygons. And then you had a couple common polygons below that little chart. The segments, and if you didn't get this drawn, it's in the book. In case you didn't get enough pictures from there. Some of you did have that filled out like you were supposed to the day before. And the triangle being a 3-sided polygon, quadrilateral 4-sided. Why those examples were at the end of that lesson is we're going to try and write those as true biconditionals. You had a couple problems like that in your homework, not necessarily on these shapes. But if we wanted to do a biconditional, what words do we use in it? Biconditional. If and only if. So we could go, a polygon is a triangle if and only if it has 3 sides. And then a quadrilateral is a figure is a quadrilateral. Maybe you'd say a polygon is a quadrilateral if and only if it has 4 sides. So those definitions can be written as if and only ifs. And I don't know if I emphasized enough for you, definitions are always true biconditionals because they go both ways. If it's a triangle, then it's a polygon with 3 sides. If it's a polygon with 3 sides, then it's called a triangle. So they do go both ways. So that was maybe a little finish up on yesterday's, but we didn't get completely done. Okay, so let's go to our lesson for today. We decided we didn't need to do that bell ringer. We just needed the state one instead. Okay, our main emphasis today is the properties, and the section we're on is 2.5. Some of these properties you have used in algebra, and what we're going to be doing today eventually is I'm going to have you do some of those same kind of solving problems that you did on like that solving worksheet. Show every step. And at every step, tell me what property you're doing. Are you doing the addition property of equality, the subtraction property of equality? What are you doing?
Didn't we skip over 2, 3, and 2, 4?
Not 2-4. 2-4 we did at the end of yesterday. 2-3 I did skip over. We will get back to it before the end of the chapter.
Okay.
But yeah, we should have your 2-4. That was the biconditionals. And I just now did a little bit on the polygons. So if you didn't catch that, either go to the e-backpack and pull up those PowerPoints again or look in your textbook. A lot of what's on your notes is from your textbook. All right, so let's talk about proof, and we're coming up with what properties are so that we can support things in what's called a proof. A proof is an argument that uses logic, definitions, properties, and previously proven statements to show that a conclusion is true. So basically, a proof is coming up with the step-by-step support behind whatever you're trying to prove. Putting ideas in a sequence so that someone can logically follow the thoughts, and giving support. Like, do you have a reason that supports you can do this or think this? So maybe it's a certain law that we've studied, maybe it's a definition of something, maybe it's a theorem, maybe it's a property. So what we're gonna eventually do is support every step in the thinking process to get from the beginning of something to the end of it. So we're really showing that a conclusion is true. An important part of writing a proof is giving justifications to show that every step is valid. If you make a logical or an argument based on things that are untrue or not logical, then it's not a proof because you haven't really given a sequence of sensible things. It's not valid. Now, proof is how you would prove some of those conjectures that we were doing. This is how you would prove them true. A counterexample could prove it false. You can't prove it true by listing examples because you would have an unending list of examples just for one idea. So to do a proof, if you can prove the correct thinking sequence and it can be supported along the way, that's how you prove something. So that's what we're going to start working on. Some of the reasons we use in a proof are properties. Now, these are some that you used in algebra solving. Addition, subtraction, multiplication, and division, all properties of equality. So you probably have a description in words, but I gave you a place to put samples or examples or in symbols. Okay, so this is what you would be writing for each of them. Okay. So the addition property of equality. If you start with two things that are equal, like A and B, then you can add C to each side. As long as you add C to each side, it's still an equality relationship. Subtraction property, start out with two things that are equal. Subtract the same amount from each side. Subtract C, and you will still have an equality relationship. Multiplication. Multiply each side by the same value, and it'll still stay equal. And the division, you can divide each side by the same thing as long as that thing is not 0, because you can't divide by 0. So divide by the same thing, and you still have an equal relationship. Now, you use these a lot in algebra, and even so far in geometry, you have used them. You would use them in just simple solving steps. So it's like, I would say, if 2x plus 4 equals, let's say 10, then what can you come up with? Well, if I subtract 4 from each side, I could say, then I know 2x would equal 6. What would support what I just did? I subtracted 4 from each side. So it was the subtraction property of equality that I did. I could even go further and say, okay, if I do this, then I can come up with another conclusion of x equals 3, supported by division property of equality. So we're really going to just put a name on the steps that we're doing, and some of the support is the list of properties that you see in front of you. So you have done those, actually, maybe not written the way that it's described. These next three, reflexive, symmetric, and transitive, you probably haven't used as much. Reflexive property, what's it say in the words for the reflexive property? An amount is equal to itself. And so you see the example, just A equals A. something equals itself, that's supported by what's called the reflexive property. You might think, why would I ever need that? Well, if you want to add the same amount on each side or subtract, like right here what I did, this technically is supported by the reflexive property. So I would use the reflexive property to get the same amount on each side and then subtraction to support it. So you're actually using that. When we get to shapes, you'll have to use the reflexive property because the segment might be a side of the first shape and a side of the second one, so you have to state it for both shapes, is what it's related to. Symmetric property, Lucas, what'd that say on symmetric property in the words on your notes?
The two sides of an equation can be exchanged.
The two sides of an equation can be exchanged. So notice what I did. I started out with A equals B, and then I just exchanged those two sides and said, okay, B equals A. Again, you did that in algebra quite a bit. Let's say you worked through a problem, and because the variable was on the right, x minus 4 equals 10, or let's see, I don't want it that way. Maybe the problem said 10 equals x minus 4, and you added 4. 4 equals x. Did your teacher say, okay, put the variable on the left all the time? That's probably how we would like it, and I'm going to set that rule. Let's put the variable on the left all the time. So how can I switch and put the x over here and 14 over there? Well, now we know that that is supported by symmetric property. So anytime you're exchanging the left side and the right side, that's referred to as the symmetric property. The transitive property, notice that one's a little bit more involved. The description that I put there, did I mention that it's like a chain of ideas? You're putting things together. In your hypothesis, you have to have two equality statements. And the right-hand side of one of them has to repeat as the left-hand side of the other. That's like a link between your two statements. So then if that links these two statements together, then we would know that the A and the C would be equal. What would an example like that be? Let's build one here on the board. Let's say if x equals 10 and 10 equals 24 minus 14, then x would equal 24 minus 14. Notice how I have this as the repeated idea that links my two statements together. So it links them and basically drops out so that the first and the last parts are equal. That's called transitive. The last one is substitution property of equality. Substitution property of equality. Substitute. What's it mean when there's a substitute for a teacher? Okay, you're replacing that teacher with someone else that's equal to them. So the idea of substitution is exactly that. You can take out something and replace it with another item that it's equal to. And you did that in algebra a lot. Okay, if you were given a problem and it maybe said evaluate x plus 10 when x equals 3. What did you do? Yeah, and plugging in is technically called substitution property. So you put the 3 in there and then you finish the problem. So you substituted when you plugged in. Okay, so we're going to try and name those properties correctly. I think I put a reminder about the distributive property. As we do some simplifying, a step that you're doing might be distributive. So I think below that chart, I put a sentence about distributive property. to remind you what that would look like. If you want to take A times the whole quantity B plus C, that's the same as A times B plus A times C. All right, some sample problems. So this is what we're going to try and do. We're going to try and prove, which means we're going to go step by step and support each idea along the way. Prove how to solve the equation 4m minus 8 equals negative 12. And we're going to write a justification for every step. Okay, so down in your sample space that you have at the bottom, you might just keep it on the left so you have room to do another one on the right. Here's how you do the proof. We're going to start out with the given equation, and you do have to write it down. You have to get that problem out of the book and write down what that would be. Okay, so write down that original problem. So what would be the first step that you would do when you're solving?
Plus.
Okay, probably add 8 to each side. So what property are we going to do when we add 8 to each side? Addition property of equality. So I'm for now at least showing the add 8 so that you can follow me. I did the addition property of equality, and this is what I came up with. Now what would you do?
Divide each side by 4.
You're going to divide each side by 4, so that you can follow, I'm going to put divide by 4, divide by 4. And what do I get? M equals negative 1, and that's supported by the division property of equality. Is the variable on the left? Yes, so I'm good. I'm done. This is an example of what's called a proof. It's the step-by-step so that someone could easily follow what's going on, and we've supported every step. Given equation, that's an acceptable reason if you are given something to start with. Now, if you have to come up with the equation, it's not going to be that it's given. So there will be some times where we have to create the equation, and it'll probably be based on some of our geometry concepts that we're doing. All right, got the first one? Okay, see what you would do here. How would you solve the equation 1/2 t equals negative 7? Write a justification for each step. How's it start out? Distributor. I'm just noticing these don't come over quite right, do they? Spacing is kind of weird. So maybe we can take time to look at that. Just notice some of the PowerPoints come over kind of strange. Transfer that. This one doesn't have very many steps. And maybe even what you are saying for the step, two people could probably say it in a different way. But what's the first thing you did? No, not divide by half. What's the first line? Get the equation in there. Yep. So the first thing would be just 1/2 t equals negative 7. That's the given equation. Okay, then what did you do? Okay, these guys divided. Anybody multiply to solve it? I would have multiplied probably. But they're dividing by 1/2, you're multiplying by 2/1. Okay, so whichever supports what you did. And I'm showing that's what I did. So mine's called multiplying, multiplication property of equality. If you did division, you're showing you divided by 1/2, and did you get the same answer? Hopefully you didn't divide by 1/2 and get negative 3.5. Okay, that one was really short. Let's try another one. This one is a little bit different, but not too much. What is the temperature in degrees Fahrenheit when it is 15 degrees Celsius? Use the equation F equals 9/5 C plus 32 and justify each step. So I don't just want you to solve for something here, but I gave you a value to use. I want you to figure out when it's 15 degrees Celsius, what's the Fahrenheit? I guess I didn't do a whole bunch of algebra ones because you just did that algebra worksheet, so you probably can support that. See if we can figure out what's different. What would you begin with? Writing the equation. Okay, let's get that given equation in there. Now, I'm not asking you to solve for a variable, but what am I asking you to do on this one? What's the temperature in degrees Fahrenheit when it's 15 degrees Celsius? I don't think well, yeah, I guess I am asking you to convert. How would you convert it? What I'm basically doing here is giving you a Celsius temperature for you to put in and then finish calculating. So right now I want to put in that 15 degrees for the Celsius. Substitution property of equality. So put in the 15, substitution property of equality. Then we're just going to do some simplifying. It's really not distributing because there aren't like two parts to multiply. Really what we're doing right now is just calculating. If I multiply 9/5 times 15, it's not the multiplication property of equality because I'm not multiplying by the same thing on both sides. I'm just simplifying by multiplying. So on this one, I just simplified by multiplying. Now I'm going to simplify by adding. So that one looks a little different. So if I'm just computing, simplify is what we're saying there. It's not the property because you're not doing the same thing to both sides. See a difference there? Questions on that one? So that was 59 degrees Fahrenheit. Looks like some are still writing, so I'm just waiting a little bit. All right. C equals that.
Oh, yeah.
Okay, that was a given equation. Okay, she's got the first line. Then what's the second one?
I didn't get that part.
What do you think we would do reading the problem?
Substitution.
Substitution, and what are we gonna put in? Now, look at this problem, it doesn't have a 15 in it, that was the last one. This one, it says, what's the temperature in degrees Celsius when it is 86 degrees Fahrenheit? So we're gonna replace the Fahrenheit with 86. Substitution, now write the whole name. And I know that you're going, well, we only have one substitution, but we're not done with all the properties yet. So put the whole name, substitution property of equality. If you want to abbreviate like what I was doing up here, substitution, subtraction, or substitution, let's see, what did I do here? So I couldn't abbreviate right. This was supposed to be subtraction, wasn't it? I'm pointing out that you should abbreviate, but I'm not getting a good abbreviation. Okay. Subtraction property, substitution property. You've got to abbreviate it so that we can tell the difference. And then I usually go property of equality instead of writing out the whole words. If you want to do the same, that would be sensible. Next step. Now you just need to do some calculating, right? So what's the first calculation you do? Okay, the subtracting probably, the parentheses. So simplify by, I call it combine like terms, you could just say subtract, so all parentheses. Okay, and then the next step, multiply, and that's simplifying. It's not the multiplication property of equality, you're just simplifying by multiplying. So I got 30 degrees Celsius.
So when we like state what property we used, if we're just simplifying, do we just write simplify next to it?
Yep. Simplifying by distributing, that could be correct, depending upon the problem, but yes. When you're just computing it, simplify would be good enough. I was just trying to tell you a little bit more what I did. That one make sense? Okay. Now sometimes we start out with a geometry idea. Okay? And so a reminder, when we write something like AB with no symbol on top, remember that meant the distance between those 2 points or the length of it. A distance or a length is really a number value. So as you're looking at those, remember geometry, that means a distance, that's a specific number. So let's try something that's a little more geometry based. If you haven't flipped your paper, if you need some more room, if you've run out of room, go to that next page, that continues this lesson. Okay, this one says, write a justification for each step, and we're supposed to solve for x. We did some problems like this in the first chapter. Starting writing, probably leave some space above it. You're probably forgetting something that needs to be at the beginning. What kind of a problem, or what kind of an equation, thinking back, would we have set up to solve for x? Yeah, Anthony? Okay, did you hear him? Okay, he said he would take 2x plus 3x plus 9, or minus 9, and it would equal the 4x minus 4.
First, so we have to draw that.
Okay, first, before that, we need to come up with what supports it, because what would support what he just said? There's a geometry idea that we need to get in here. Got your chapter 1 notes handy? Let's pull those out. Chapter 1 notes. We're going to search for a geometry relationship that is called segment addition postulate. If you were good at chapter 1, maybe you've got segment addition postulate in your brain already, but not everybody is out there. Segment addition postulate. Take a look at what that was saying and see if you can relate that to this problem so we can get the geometry concept stated first. Everybody find that segment addition postulate? What section is it in?
That's right, it's on the third
1, 2.
page.
1, 2? Back side of 1, 2? Okay. All right, so look at the kind of statement that is there. It had like, if B is between A and C, then AB plus BC equals AC. We make that kind of statement with our diagram that we currently have. Because I see in the picture that M is between N and O. What did you want to say? Oh, did you want to tell me what it was? No? Okay. What's our statement that I'm looking for?
If N O equals 4x.
No, just the segment addition. What distance plus what distance equals what distance? Just naming it. So I'm looking for something like NM plus MO equals NO. And looks like I wrote the NO first. NO, the whole thing, equals the length of NM plus the length of MO. This is the geometry idea that's going to help us get to the equation that Anthony wanted us to have just a little bit ago. Segment addition postulate supports it. Chapter 1 concept. Now how do we get from this idea to what Anthony basically was telling us is by substitution. So substitution property is what I'm doing next. What am I going to substitute for NO? Look at the picture. What's NO equal to help me get an equation? 4x minus 4 equals, what's NM? 2x plus 3x minus 9. So it's in the other order than what Anthony said, but he gave me the right equation, but we had a couple thoughts that we had to support to get there. Question about that geometry step at the beginning? So look at the kind of problem and information and what that first step was. That might help you as you try and do some on the homework. Now, once we got it substituted, we're pretty much to our solving and just giving the reasons. What would you do probably first? I would probably simplify over here, so I do some combining like terms. And now you've probably got 4 choices. I think what I did, can you tell what I did? How did I get from this to that? Okay, so to get it on the other side, what did I really mathematically do? Subtracted 4x. So I subtracted 4x from each side, so my support should say subtraction property of equality.
Then won't you have to switch it again at the end anyways?
Yeah, we will need to. I mean, anyways, now anytime I switch it, I have to say what property allows,
So,
and I only want to do one property at a time. So
same like when you do the equation, if you would have added to the other side,
Yeah.
would it have still worked the same?
Right. If I would have had this set up the other way, it would come out with the variable on the correct side, but I wanted to force us to do the symmetric property. So I set it up this way so that you have to see that. All right, she's thinking ahead about something here. Next step would be, not divide yet, add the 9 to each side. So what are you gonna get when you add it? If you wanna put the +9 +9 so you see it, that's fine. So you're gonna have 5 equals x, and that was supported by, no? What did we do to get this? We added 9 to each side, so addition property of equality. Now the idea is that Morgan was thinking, and that I think Jacob was saying, we wanna switch it around, right? Because what did I say for the rule? The variable on the left. So I want to switch it, instead of 5 equals x, I want it to say x equals 5. What supports the fact I can do that? Symmetric property of equality. And Morgan was saying, why didn't you just start it differently? Well, it's because I wanted to force us to see that symmetric property on there. Okay, questions about the steps through there? Let's see what you can do on this example. There's one that's angles. So let's look and see what else there. And it's a geometry diagram, so I'm probably going to have a geometry concept to get us started. And then we can do some substituting. So let's see what we can do. Start the last one with. What was the support? What was the first support? The first support on that last one, the first reason. Not the statement, I'm asking kind of what the reason is. What was the reason part? On the right hand side, the first line in that last example? Segment addition postulate? Can you do segment addition postulate on the example that we're on now? Are there segments there that you want to add together? No. They are angles. How about you look at the angle addition postulate? Do these always start with one of those postulates? No, but I'm trying to give you a hint. Same chapter 1. Got a few more sections. There was an angle addition postulate. And you write a statement based on that relating to this diagram. Measure of what angle, plus measure of what angle, equals measure of what angle. You're naming them. first step is just naming them. That's what the angle addition postulate has you do. So name those angles, then we'll bring in the substituted values. You should have a line before this. This is angle DBC. M for measure. Measure of angle DBC. If you're stuck, how about that? And maybe if you were doing it on your own, maybe you got it in the other order. Not that that's wrong, this is just the way I had done it. So I put the measure of that whole big angle, ABC, is equal to the measure of the small angle, ABD, plus the measure of angle, DBC. When you're talking about their measures, put the M in front of it. Kind of looking at the last one, what should we do next?
We should fill in with the actual.
Okay, fill it in with these expressions that are here, which means we're doing substitution. So substitution, property of equality. Next thought. What'd you get for your next line here?
For my next line, I have minus or plus 16. I added 16 to both sides.
Okay, so you added 16 to 8x?
Yep.
What'd you come up with?
16 plus 8x equals 3x.
Oh.
5 plus 6x, and then I did
Okay.
minus 5, which gave me 11 plus 8x.
Sounds like what you're doing is okay. I would tell you it's not exactly what I did, so yours will look different than mine. Did you put reasons beside your lines there? It looked like you just had to solve it. Okay, what we're really emphasizing today is what's the reason, what's the support. Okay, so I probably combined like terms over here. So that would be just simplifying. And then I added subtracted 9x from each side. And then because of the -1 here, I divided each side by -1. And my variable is on the left, so I'm good. Now your steps might have looked a little bit different, but are you getting the support for what you did? You probably have some similar supports to what I had. Why don't you show me a thumbs up, down, or sideways? How are you doing in understanding what I'm trying to show you here? You getting pretty good? Okay, looks like you're doing pretty good. Question on that one? Okay, then the last part, there's a reflexive, symmetric, and transitive property of congruences. It's not always equality. That's why I wanted you to write the whole name, so that, like reflexive property, there was one of equality, but there's also one of congruence. So what's the difference between the reflexive property of congruence and the reflexive property of equality? It just depends what kind of symbols are in it. When we have congruence, then we're naming the actual segment EF. So segment EF is congruent to segment EF. A segment is congruent to itself. An angle is congruent to itself. So pay attention to what symbols are there. Is it the property of equality or congruence? Symmetric, remember you could switch the two sides, just with congruences. For instance, if angle 1 is congruent to angle 2, then angle 2 is congruent to angle 1. You can switch the sides in congruence relationships. This transitive, remember how I had that connection up there? I had to make it so that it repeated and hooked it together, that kind of idea. You can do that in congruences also. So if segment PQ is congruent to RS, and that same segment RS is congruent to a third thing, segment TQ, TU, then the RS links it but drops out. So segment PQ has to be congruent to segment TU. Transitive, I kind of remember that as a train. It's kind of like the caboose, then there's a car, And then that car hooks you to the, or excuse me, I shouldn't say caboose. How about engine? Engine and then the cars of the train and then the caboose. So isn't the engine really connected to the caboose? All of those in-between things? That's just a way that I kind of remember it. Numbers are equal, figures are congruent. These are numbers because it's distances. Measures are numbers, but the actual angle or the actual segment is when you use congruent. So let's try just a little examples of those properties. Now these are either reflexive, symmetric, or transitive, of equality or of congruence. So first one, with this symbol, it's going to be a property of congruence. That angle is congruent to the very same angle. Reflexive property of congruence. Next one. Now, instead of if then, I wrote it a little different. Measure of angle 1 equals measure of angle 2, so measure of angle 2 equals measure of angle 1. Of what?
Of equality.
Of equality. Okay. Symmetric property, but it's of equality. Okay, third one. That's congruent to that. The same thing's congruent to EF. So A, B, and EF are congruent. Very good. Transitive property of congruence. 32 degrees equals 32 degrees. Correct. Want to try them on your own, or are you doing good here? Doing good? Okay, how about first one?
Addition properties.
What'd you say? Not addition property. We're not adding anything to each side.
Symmetric.
Symmetric. All we're doing is switching. What's on the left becomes on the right. So the left and the right are being switched. Symmetric property of equality. Right. Making people think it's kind of in here. Number 2.
Reflective property.
Reflexive property of
Equality.
equality. 3. Okay. That one could be substitution because you could think, oh, I'm going to take out the A and put X there in its place because they're equal. So that could be a substitution also. How about the last one?
Congruence.
Good. All right, so we've got properties kind of figured out. We know how to do the step-by-step. Start it with the given equation and then tell what property you're using as long as you're doing the same thing on each side. I would have multiplied by 6 and then added 5. Some of the problems you had to, oh, here's one that uses distributive. We didn't have an example that way. I know you won't really get started on your homework in 2 minutes. So notice how this one has a distributive property in it. We had the given equation, we distributed, then what did I add to each side to get this one? Follow what I did without me showing it? What did I add to each side to go from here to here? I added how much? 2R. I added 2R to each side. Then to go from there to there, I did another addition property of equality. Added 3 to each side. And then what did I divide by? 8. So I should be able to follow it, but sometimes it helps having that little extra step in there. And you were doing really good on the properties, so I think you got that. All right, the problems that you are to do over, I guess, your 3-day break. Yes, page 107. 1 through 11. I gave you the odds because I like those problems better. I'm kind of scared of doing that sometimes, but what you need to do is be sure to give the reasons. That's the whole emphasis of this section. is not just that you can solve those algebra problems, but can you support each step that we're doing? So it is very important. Can't write it down? You can't write it down? Is that lazy? Good, great. You need it on a sheet of paper anyway. So give the reasons for each of those steps along the way. If any of you are preparing for a retake on your test, you might make a note to yourself that you need to work on chapter 1, preparing for your retake. So there might be some things in chapter 1 you need to look back to as you get started on a few of the problems. And if the variable's not on the left, get it so that it's on the left. All right.